In the last video we introduced row operations on matrices. The motivation for that was that row operations on the augmented matrix of a linear system were supposed to parallel the effects of manipulating the equations in that linear system in the usual ways which we do when we're solving linear equations. I've written on this first slide here an example of doing that. If you start off with the linear system 3x plus 4y is equal to 6 and x plus 2y is equal to 5, then the augmented matrix would be this matrix on the right here, 3, 4, 6, 1, 2, 5. The first manipulation that we used in our example where we solved those equations was to subtract 3 times the second equation from the first equation. In other words, to eliminate x from the first equation. When we did that, the system of equations we got was minus 2y equals minus 9 and x plus 2y equals 5. Again, that's what happens when you subtract 3 times the second equation from the first equation. But if you look at the effect on the augmented matrices, well, that is precisely subtracting 3 times the second row from the first row. In other words, it is doing the row operation which subtracts 3 times row 2 from row 1 to the augmented matrix. In this video we're going to look at another way of understanding the effect of row operations on matrices. What we will show is that row operations are actually implemented by matrix multiplication by things which we're going to call elementary matrices. Here's the definition of an elementary matrix. An elementary matrix is one you can get by doing a single row operation to an identity matrix. Here are some examples. If you take the identity matrix I2, you will remember that the I2 is the identity matrix 1, 0, 0, 1, and then apply the row operation which swaps row 1 and row 2, then what you'll end up with is this matrix here. So this is an elementary matrix arising from doing the row operation which swaps row 1 and row 2 to the 2 by 2 identity. For another example, the elementary matrix here arises from doing the row operation which adds 2 times row 2 to row 1 to the 3 by 3 identity matrix. Again, you can see if you write down the 3 by 3 identity matrix here and add 2 times the second row to the first row, then what you'd end up with is this matrix which I've written in the example. Finally, if you take the 2 by 2 identity matrix and you do the row operation which multiplies row 1 by minus 1, what you get is this matrix here. So these 3 things are examples of elementary matrices. Elementary matrices are what you get if you do a single row operation to an identity matrix. Here's the reason to be interested in elementary matrices. It's because if R is a row operation and A is an n by n matrix, then doing the row operation R to the matrix A is the same as taking the elementary matrix which you get by doing R to the identity matrix IM and then doing matrix multiplication of that times A. This theorem tells you that doing row operations to a matrix is the same as multiplying by an appropriate elementary matrix. I'm not going to run through a full proof of this theorem here because it's not particularly enlightening and it takes quite a lot of notation to write down. If you'd like to see a complete proof, you can find a complete proof in the online notes for this section. What I'll do instead is to do an example to show hopefully why this theorem is true. So we will pick the 2 by 2 matrix A, 1, 2, 3, 4. We will pick the row operation R, which will be the row operation which swaps row 1 and R2. Then what the theorem claims is that doing R to A should be the same as doing R to the identity matrix, which would result in 0, 1, 1, 0, and then matrix multiplying that into 1, 2, 3, 4. We're going to verify this simply by doing the matrix multiplication on the right and applying the row op on the left and seeing if we get the same thing. So this matrix multiplication is easy enough. If we want to work out the 1, 1 entry, that would be the first row of the elementary matrix multiplied into the first column of A, so that would be 0 times 1 plus 1 times 3. The next entry will be 0 times 2 plus 1 times 4. And the bottom left entry, the 1, 2 entry, the 2, 1 entry, would be 1 times 1 plus 0 times 3, that's 1. And the 2, 2 entry would be 1 times 2 plus 0 times 4. So that's this. And you can see that this really is equal to what you get by taking the matrix A and applying the row operation which swaps row 1 and row 2. If you swap row 1 and row 2 in the matrix A, then you really do have 3, 4, 1, 2 as we've got here. So this really is equal to R of A. So this is an example of what the theorem says. If you want to see a complete proof of this, it's a little bit tedious to write down, but you can find it written down in detail in all 3 cases, so for all 3 different types of row ops in the online notes. The importance of that theorem is that it has a very useful corollary which says that elementary matrices are invertible. This is incredibly useful because, as you will see in the next few videos, this helps us very much in our quest to determine when matrices are invertible. Let's try to do a proof of this corollary assuming the theorem on the previous slide. The proof comes from using the observation that we made a little while ago, which was that if R is a row operation, then it has an inverse row operation S. So take a row operation R, and what we need to do is show that the elementary matrix, so that is R of IN, is invertible. In order to do that, we need the fact that R has an inverse row operation S. And what we're going to do is to show that the inverse of the elementary matrix R of IN is S of IN. So what we need to do then is we need to show that R of IN times S of IN and S of IN times R of IN are equal to the identity matrix. That's what you need to do to show that R of IN, the elementary matrix, is invertible and that its inverse is S of IN. What the theorem on the last slide allows us to do is to rewrite the product R of IN times S of IN in a different way. It allows us to say that this is the same as R of S of IN. You'll remember what the theorem said was that applying R to a matrix A was the same as doing R of I times A. So using this theorem with A being the matrix S of IN, what we get is that R of IN times S of IN, that's the right-hand side of this equation, is the same as R of S of IN. That's the left-hand side when A is replaced by S of IN. But of course we chose R and S to be inverses to one another, so doing S then doing R is the same as doing nothing. So what we have is that R of IN times S of IN is equal to the identity matrix IN. But of course the same argument works exactly the other way round. S and R are inverses of one another, so we can simply apply this argument the other way round to get that S of IN times R of IN is the identity matrix. And then what we know then is that R of IN times S of IN and S of IN times R of IN are both equal to the identity, so they're inverses of one another, and that means in particular that R of IN is invertible and its inverse is S of IN.